In this module, we will consider impulse and momentum. In principle, all physical processes can be described solely in terms of forces and their effect on objects. But even relatively simple systems can be difficult to solve by relying only on forces and Newton's laws. It turns out that Newton's third law allows for two simplifying approaches to understanding physical processes, both embodied in what are called conservation laws. The second of these is conservation of momentum. In order to understand conservation of momentum, we first must define the concepts of impulse and momentum. Newton's second law gives us that the sum of all the forces acting on an object is equal to the mass of the object times its acceleration. And of course, we can write the acceleration in terms of the time derivative of the velocity. Since the mass of an individual particle is not going to change, we can bring this mass inside the time derivative, and we obtain the time derivative of something called the momentum. That is, the mass times the velocity. For collections of particles that may be grouped in changing ways, it turns out that momentum is a much more useful quantity to work with than velocity alone. Impulse is the integral of force over time. So if we take Newton's law written in terms of momentum and multiply both sides by dt and integrate, we find that the net impulse delivered to an object is equal to the change in the object's momentum. This is a result which is very closely related to the work kinetic energy theorem. Recall that the work is the integral of force along a path in space, and the total work is equal to the change in kinetic energy. Well, the impulse is the integral of force over time as an object moves along some path, and this is equal to the change in momentum. The concept of momentum is most useful when applied to a collection or a system of particles. Consider a simple system of two particles in a gravitational field and interacting via some force between the two particles. So we have illustrated first a particle of mass 1 with a given momentum. We're also going to have a second particle of mass 2, and it has its own momentum. Acting on both particles is the force of gravity acting down. And acting between the two masses is going to be some unknown force, F, where we have F12 is the force on mass 1 by mass 2, and F21 is the force on mass 2 by mass 1, and by Newton's third law, F12 is minus F21. These are an action-reaction pair of forces. If we consider Newton's second law expressed in terms of momenta for each of the particles, we obtain the two equations. The first, that the force F12 plus the force of gravity on particle 1 is equal to the time rate of change of the momentum of particle 1, and a similar equation for particle 2. Now, if we add these two equations together so that we put the forces on the left-hand side and the time rate of change of the momenta on the right-hand side, we see that the forces acting between the two particles cancel out because of Newton's third law, and we wind up with the equation that the force of gravity on the two particles is equal to the time rate of change of the sum of the momenta of the two particles. So when we treat the two particles together as a system, the total momentum, which is the sum of the individual momenta, is only affected by forces that are external to the system. In the context of momentum, an isolated system is one in which no external forces act on any particle within the system. Newton's third law guarantees that for an isolated system, the total momentum of the system remains unchanged. This is our concept of conservation of momentum. Even with no knowledge of the internal interactions of a group of particles, conservation of momentum allows us to know a great deal about how that group of particles behaves. Even in the presence of external forces, conservation of momentum can often be a valid approximation. Consider two particles colliding or an object exploding. The forces acting between the particles in the system will tend to be very large, but will only act for a very short amount of time. If the internal forces acting on each particle are much larger than the external forces, then the internal impulse acting on each particle will dominate over the external impulse. During the short time interval when this is true, we can ignore the external forces and assume total momentum is approximately conserved. Consider the following example. You and a friend throw two balls up into the air and try to make them collide. Both of the balls are going to follow a ballistic trajectory. That is, they're going to undergo projectile motion. During this time, gravity is acting on them. It's making them follow a parabolic trajectory. But just before the collision occurs between the two balls, measure the momentum of each ball. This gives you some initial conditions that you can use for conservation of energy to help you understand what are the final momenta of the particles just after the collision. The collision is very, very brief, and during this collision process, gravity does not have time to appreciably change the motion of the particles. So the collision causes the particles to redirect their motion, and conservation of momentum allows you to figure out what this redirection is. After the collision, with the knowledge of the new momenta of the particles as initial conditions, the particles will then again follow a ballistic trajectory. You can use the equation for projectile motion and follow the parabolic trajectory of the particles as they move away from each other.